Welcome everyone to lecture 5.7. The title is Lagrange multipliers, but I want to also subtitle this a better way to do optimization on the boundary. So in this lecture, we're going to learn a new technique for optimizing multivariable functions called the Lagrange multipliers method. And our two goals in this video are to define the Lagrange multipliers method by way of a constrained optimization problem. And we'll set this up as a minimum and maximum problem, or an optimization problem of a function that's subject to a constraint. We'll see what this is in the first two slides. And if necessary, and actually most of the time it will be advantageous to use Lagrange multipliers to solve that constrained optimization problem. In the context of lecture 5.6, where we had a closed bounded domain to perform optimization on for a multivariable function using the extreme value theorem as our theoretical tool, we often had to perform some sort of substitution on the boundary to simplify the function and then find critical points on the boundary. Lagrange multipliers will be an alternative method for doing that step in the optimization procedure. And in many circumstances, it will be a better method, but we'll see that it can be complicated sometimes as well. So to get started, what does it mean to have a constraint on our optimization problem? So sometimes we're not interested in maximizing a function over an entire closed bounded region in the XY plane or in higher dimensions. We might just want to restrict our focus to the points that satisfy a constraint equation. And in practice, that constraint equation may define the boundary of such a region that we learned about in the last lecture. If we apply the constraint, what we're doing geometrically is saying only look at the f of xy values on the points that satisfy this constraint. And if that constraint defines a curve, for example, this could be a cross-section of our surface, z equals f of xy, but more general constraints are possible. We could have only those points satisfying a few different equations, and we'll see how that works towards the end of the video. And that could define not just one cross-section, but multiple independent cross-sections. So one thing that's worth noting right up front is that the maximum value of a function on the constraint on that slice of our picture is unlikely to be the global maximum of the function everywhere. The global maximum could very well occur at a critical point, which is where the gradient of the function f is equal to 0. But we can still use the gradient to find the maximum on the constraint using a little bit of geometry that we learned about back in the gradient section. So the picture here, by the way, shows an actual cross-section of this blue surface, z equals f of xy. Looks like a downward facing parabolic surface. And it's subject to the constraint given by this gold curve, which is defined by x plus y equals 1. Now, in general, the equation x plus y equals 1 defines a plane. So what we're really seeing here is the plane x plus y equals 1, which would be stretching infinitely in both directions, slicing through the surface and defining just that golden curve on the surface. How do we solve constraint optimization problems? Well, the following theorem, which we'll call our Lagrange multipliers method, gives a theoretical tool that allows us to solve these relatively easy and in many circumstances, easier and faster than the previous methods we developed last lecture. So the theorem says that suppose we're given what's called an objective function. We'll think of this as the function we want to optimize, f of xy, and separately a constraint function, g of xy, and suppose that these are both differentiable functions. Then the local extremes of f, given the constraint g equals some constant c, occur where the gradient of f is equal to lambda times the gradient of g for some number lambda, or where the gradient of g is equal to 0. This number lambda that appears in the formula is called a Lagrange multiplier. You should think of this as saying that the gradient of f is parallel to the gradient of g, and the Lagrange multiplier lambda is the factor that allows you to multiply from one to get the other. So nabla f, the gradient, is a scalar multiple of nabla g, the gradient of g, and that scalar factor is the Lagrange multiplier lambda. By the way, this theorem generalizes immediately to functions of any number of variables. Technically, this could also work in one dimension if it was a function of a single variable x, but constraints would define finite sets of points for the most part in the one variable situation. So we'd end up just testing endpoints anyways, and then the gradients aren't so interesting at those points. So this theorem allows us to theoretically guarantee the existence and location of local extrema of a function. But the point is that once we apply a constraint g equals some constant, you should think of this as a level curve of a function g of xy. Once we apply this constraint to the domain of f of xy to restrict to some curve or hypersurface in higher dimensions, then this provides a complete list of all of the possible places on that boundary where the extreme values can occur. And by testing all of the resulting points, we can find the absolute extrema, the absolute minimum and the absolute maximum of the function. So this will be one of our tools in assembling a list of points to test at the end of optimization problems. And this is what we're going to study today. So I wanted to give a visual demonstration of why the theorem makes sense. And one thing we learned about when we defined and studied the properties of the gradient originally is that the gradient is pointing in the direction of greatest increase or decrease of the function. And in general, the gradient vector will point uphill in the steepest direction, but the negative gradient vector, or traveling in the opposite direction, will point in the direction of greatest decrease, or point straight downhill. And what this means in practice is that if we have level curves of our function, we can think of level curves as particular constraints. But if we have a constraint that happens to be a level curve, then the gradient function will be perpendicular or orthogonal to that level curve at any given point on the level curve. More generally, if we define a constraint function g and set it equal to a constant c, and then we look at the values x comma, or the points x comma y that satisfy this constraint and also lie on the surface f, or z equals f of xy to be more specific, then the gradient vector of f, which is perpendicular to all level curves, will also be perpendicular to this, this cross section, g equals c. It's a level curve of the function g, but the points that satisfy the equation defined by f as well will live on the surface f. And in that particular circumstance, the gradient of g, which is perpendicular to the level curves of g, should be parallel to the gradient of f at the points that are maximum, that are local max or local min values for f with respect to the constraint g. We can spell this out in a little more detail by looking at directional derivatives, but I'll leave it to you to read this in the textbook if you want to know a little more. And for our purposes, the theorem will be enough. So this is a geometric explanation for why we get an equation like the gradient of f is parallel to the gradient of g. It's an easier way to say that. Or the gradient of f is proportional to the gradient of g by some constant lambda. Let's go practice with this method to see that it gives us a list of values to test. So here's a constrained optimization problem. We're looking for the maximum of a function f of xy given by that formula, subject to the constraint that the coordinates satisfy this elliptic equation, 4x squared plus y squared equals 4. If you want to try this on your own, it would not be a bad idea to set up the problem, and here are the ingredients that we'll need. We need the function f of xy, which is given to us. We also need a function g that we can use to constrain the optimization problem. And then I've reminded you of the Lagrange multipliers equation here, but you need to compute each piece. So pause the video now and try to at least start the problem without me, and then I'll catch up and show you how the solution goes. All right, so we're given our function f. We know that our g function, the constraint, should look like, in the given problem, should look like the level curve of some function g. So I see a good candidate here, which is 4x squared plus y squared. And notice that it's set equal to a constant 4. So that's giving our level curve of g that acts as a constraint on the surface f. Our Lagrange multipliers equation is then given to us. And in order to compute the pieces of this equation, we want to compute the two gradient vectors. So nabla f, if I take the derivative, the partial derivatives of f with respect to x and y, I'll just get those variables in the opposite order. excuse me. Then we'll have some constant lambda times the gradient vector for G. And luckily, G has a pretty easy gradient to compute as well. We'll get in the first component 8x, and in the second component 2y. And this is the part where, hopefully up to here, this is pretty familiar, but this is the part where it'll require a little bit of practice. And I want to show you a couple examples in this lecture so you get comfortable with what to do next. So I'm going to take the functions away for a moment. What we're looking for now are points x comma y that satisfy this equation, which is an equation of vectors, meaning we can set each of the two components equal to each other. So I'm going to do this in two steps. On one hand, the first component of each vector has to be equal. So y is equal to 8 times lambda times x. And on the other hand, I'll even write and, because both of these two things have to be true. The second component, x for nabla f and 2 lambda y, have to be equal for these vectors to be equal. So we're looking for points x comma y that make those two things true. And we're going to play these two equations off of each other in order to solve for x and y. And it just so happen that we can completely solve for x and y only using this information, but in many circumstances, we'll want to use the original information as well. In particular, the constraint. Because this is set equal to 4, this constraint will help us determine possible x and y that satisfy all of the equations above that give us possible maximum and minimum values. In this problem, we're only looking for the maximum, but we'll end up getting full information by testing all of these points at the end. So let's do it. One of the easiest ways to solve equations like this is to solve for one variable. And sure enough, we've solved for y, where we didn't have to do anything, and then plug it in the other equation and try to extract information about the other variable. So in this case, we'll get the equation x equals 2 lambda times 8 lambda x, which I can rewrite as 16 lambda squared x. And this point, so x equals that quantity. At this point, you'd say, oh, let's just cancel out x, divide out by x, and solve for lambda. There's a good reason not to do that in these problems. And in general, I encourage you to not divide by any symbols, x or y or lambda, in these problems. And in a later problem, we'll have 3 variables, and we won't want to divide. The reason being that x could be 0. It's possible that x equals 0, y equals something gives us a valid solution to this equation. And it's also possible in other circumstances for lambda to be 0. So we don't want to divide as much as we can avoid it. Instead, I'm going to solve for 0, one of our favorite tricks, by subtracting these two quantities. And I'll immediately factor out an x. So I'm subtracting these two parts of the equation. I'll factor out an x, and this is all set equal to 0. This is a form that we can actually extract information from, because we see on one hand that x could be 0. So again, it's possible for x to be 0, and we want to account for that possibility. On the other hand, if I solve for lambda, this will tell us that lambda is equal to plus or minus 1/4. And you can do both of these carefully. The x equals 0 you can see for free. The solution for lambda you can do carefully in a couple steps if you need. So let's actually run with both of these possibilities. If x equals 0, we need to go back somewhere up above and use all of the equations we're handed in order to deduce what possible points satisfy this equation. So I'm going to look here actually and notice, and maybe I should switch to a different color for this part. So let's go with blue. So notice here that if x equals 0, y also has to be equal to 0. But there's a strong possibility that this point does not satisfy the constraint equation. And if we go back to the start of the problem, the constraint was that g of x, which is 4x squared plus y squared, has to be equal to 4. And we can quickly see that this is not true. So 4 times 0 squared plus 0 squared is equal to 0, which is not equal to 4. So this point, despite appearing to be a possible critical point or possible point to test on the boundary on this curve, actually doesn't work because it doesn't even live on the constraint elliptic equation. On the other hand, let's see what lambda equals plus or minus 1/4 gives us. So if lambda equals plus or minus 1/4, then we have our choice. We can really use either of the two equations. So I'm going to stick with blue to use this equation. And if I write things as y equals, let's see, 8 lambda times, lambda is going to be plus or minus 1/4 times x, this means that y is equal to plus or minus 2x. And we have a constraint equation that we can go appeal to see what happens. So 4x squared plus y squared, which is now plus or minus 2x, quantity squared, has to be equal to 4. And this is now an equation just in terms of x, and we can actually solve. If you square this out, you'll get just positive 4x squared again. So I really have 8x squareds on one side and a 4. And if I solve for x, I'll get plus or minus 1 over square root of 2, which is also known as square root of 2 over 2 if you prefer. Okay, so that gives us our x coordinates that are possibly going to give us max or min values. And in fact, by the Lagrange multipliers theorem, these are the only possible x coordinates. And now the goal is to figure out which y coordinates correspond to these x coordinates. And I'll circle the information I'm going to use. And I advise you to be very organized in how you're writing things down. And I'm out of space, so this should be near the end of the problem. If x is plus or minus 1 over root 2, and y is given by plus or minus 2 times those x coordinates, then y has to be equal to plus or minus 2 over root 2, and that's easier to write as just square root of 2 in the numerator. So this gives us a list of all of the possible x and y coordinates, excuse me, and then we're going to need to go test those. So just to write these things down, the possible locations for the maximum of this function, which are also the possible locations for the minimum, are the following points. The x coordinate can be positive 1 over root 2, and the y coordinate can be positive or negative square root of 2. And also the x coordinate can be negative 1 over root 2, and the y coordinate can be positive or negative root 2. So this is a list of possible locations. And now what we're going to do to finish the problem to find the maximum value of f is to test each of these points by plugging them into the function. And that'll give us a collection of values, and we just pick the largest value. That's the end of the problem. This is step 3 in our method that we talked about for the last lecture. So let's test all of these points. I've got our list, and we'll write down which one's the maximum. F of 1 over root 2 times root 2. And notice that the function is just multiply the two coordinates together. Luckily, I have written things down in a way that's easy to multiply them. Root 2 over root 2 is just going to give us positive 1. Let's see what's next. 1 over root 2 times negative root 2. Those will cancel out and give us negative 1. Negative 1 over root 2 and positive root 2 will give us negative 1 again. And finally, negative 1 over root 2 and negative root 2 will give us positive 1. So the maximum value of the function f equals xy, subject to that constraining equation, 4x squared plus y squared equals 4. So around that elliptical boundary, maximum value of this function is 1, positive 1 is what we got. And we could also write down the minimum value. Since we see it on the list, it's negative 1. And it occurs at 2 places for each of the max and min values. And you can go back and try to draw this ellipse and highlight those points. We'll do some of these in class together as well. So there we go. It's our first real constrained optimization problem using Lagrange multipliers. And notice that, just to point one thing out compared to the last lecture, if I didn't have this Lagrange multipliers method, I would have had to somehow reduce the complexity of our function f equals xy using the constraint, and that would involve solving for x or y in the elliptic equation. And that's going to have a whole bunch of plus or minus square root nonsense. And then it'll be difficult to maximize that function using old-fashioned single variable calc methods. So this is in many circumstances, such as this one, the Lagrange multipliers method using gradients is a much cleaner method to identifying the list of possible critical points. Let's keep going and see how far we can push this method in this lecture. By the way, here is an actual depiction of what's going on in the previous example. The gold curve is our constraint elliptic equations. This is an ellipse, and you can figure out why it is fatter in the vertical direction than in the horizontal direction based on its equation. At the critical points, which we just determined were 1 over root 2, and plus or minus in both coordinates for those. These are the 4 points that we found. For the plus or minus versions, the gradient nabla f is pointing in the same direction as nabla g. And that means that if we compare them, the lambda value will be positive. Those are the lambda equals positive 1/4 ones if you go back and solve for lambda. And on the other hand, at the negative positive or positive negative xy coordinates, the gradient of f was pointing in the opposite direction of the gradient of g, and the lambdas there were negative 1/4 for each of these. So you can go back and solve for those explicitly using all the equations we had previously. So these 4 points all satisfy the Lagrange multiplier equation in addition to the constraint, and they maximize or minimize the function here. And the main takeaway from this method is that the level set of a continuous constraint function is always closed. And by level set, I mean the g is set equal to some constant c. And if it's also a bounded set, such as this ellipse being bounded, its fixed distances or maximum distance away from the origin is something like 4, then the Lagrange multipliers method will always help us identify the global maximum and global minimum of the function on that constraint, on that boundary curve. Here's another problem that we can do. We said that the theorem applies to higher numbers of variables, so let's practice with one of these equations right away. We have some function f of x, y, z defined by this equation that's defined just on the sphere, which is the set of points in x, y, z space satisfying x squared plus y squared plus z squared equals 36. Since 36 is 6 squared, you can think of this as all of the points in 3 dimensions that are a fixed distance of 6 units away from the origin. This is explicitly what a spherical equation tells you, since the distance formula in 3 dimensions looks like the square root of the left side of this. So here's our sphere highlighted in teal. And using the Lagrange multipliers method, we can identify the sphere as the graph of the constraint equation. This will be our g in a moment. We'll do this together on the tablet. All of the vectors nabla g will end up being perpendicular to this level set. This is now not a level curve, it's a level surface for a higher dimensional function. We want to identify the points where the gradient of f is pointing in the same direction or the opposite direction as the gradient for g. And by the Lagrange multiplier theorem, those will be our points to go test. So you can imagine drawing what's called a gradient field, drawing all of the little arrows for nabla f, pointing in all the different directions possible at every point on the sphere, and then just visually checking where they appear to line up with nabla g, the gradient for g. But algebraically, we can do this using the equation in the theorem. So I'm going to switch over and do this one together. But I encourage you to pause the video right now before you see too much of the solution. And let's see. I need to scroll down to the problem and try to work as much of this out as possible on your own. So here is a reminder of what the function is. I told you what the constraint is. It's the part of the word problem that's set equal to some constant. So in this case, the function x squared plus y squared plus z squared has level set that sphere pictured when we set this equation equal to 36. And then we want to implement Lagrange multipliers by evaluating the following formula involving their gradients. So I'm going to take a drink for a moment and see if you can work out at least the gradient part of this problem and set up the equation in the Lagrange multipliers theorem. All right, let's do it. So we've got our equations. We need to compute some gradients. And for f, I'm going to leave a little bit of space. This appears to be complicated. It's more complicated than the previous problems, f, but it's not so bad in terms of derivatives, since when we hold 2 variables constant and vary the third one, this just becomes a power rule problem. So when x is the variable, we'll bring down the 4 times x cubed, and then the other variables are constants, so we just leave those powers alone. Likewise, when y is the variable, we'll bring down a 4, leave x alone, and z alone. And then finally, when z is the variable, this one's really easy. It's a constant times c. So that's the left side of the equation. G has a really easy gradient since it's just 3 different terms added, and we'll get 2x, 2y, and 2z. So what we really have here is And I'm actually going to immediately write out the three equations we get. Is we have these two gradients identified, and we want to figure out which x, y, and z make these vectors point in the same or opposite directions. So let's do it. I'm going to write out the first, second, and third components set equal to each other. So we have 4x cubed y to the fourth z is equal to the first component of lambda times nabla g. That's going to be 2 lambda x. In the middle component, we have 4x to the fourth y to the third z is 2 lambda y on the right side. We have x to the fourth y to the fourth is equal to 2 times lambda z. And I also want to remember one more equation, the constraint x squared plus y squared plus z squared is equal to 36. So this is all of the information that we're given essentially, and this is what we need to use to solve for x, y, and z and find all the points that satisfy these equations. So like I cautioned in the previous problem we worked on together, we don't want to divide out by things. So here I see there's a common factor of x, and we could actually subtract and factor out 2 times x and go from there. But then there are still pretty complicated expressions left over in terms of x, y, and z. So here's another method that I want to teach you, which is try to use the Lagrange, the lambda part of the equation, to relate the left side, the components of the gradient of f, directly to each other. For example, if all of these three expressions were equal, then we would have equations just relating the left sides, which only involve x, y, and z, and we can at least get rid of lambda for the moment. But we don't have the lambda parts equal, so what we can do is multiply through by other variables to make them all equal to each other. So let's multiply to get a common expression on the lambda side of the equation. I'm going to do this as follows. Let's actually copy paste our starting equations, and we'll keep the constraint in mind when we need to check for points that actually satisfy that constraint. But let's take each of these equations and multiply it by something so that the right side is identical to the other equations, right sides. And in this case, let's try to go for 2 times lambda times all three variables, x, y, z. I already have an x, so I need to multiply by a y, z in the first expression, and I'll multiply the entire equation through by this. I already have a y in the middle one, so that'll be xz missing. And I already have a z here, so that'll be x times y. So let's actually rewrite each of these equations when we multiply through by the things indicated and see what we get. So here I'll have 4 times x cubed times now y to the fifth and z squared is equal to 2 lambda x, y, z. The middle equation now reads 4 times x to the fifth times y cubed times z squared is equal to 2 lambda x, y, z. And already this is new information. This says that these two are equal. We'll capitalize on that in a moment. And then in the last equation, we have x to the fifth, y to the fifth is equal to 2 lambda x, y, z. So you may not have thought to do this before seeing my suggestion, but this is now a trick that you can use in future problems. So I want to really lock that in as a possible technique to use. So again, the right sides of the equations are now all equal. That was our objective a moment ago, and this gives us new information. In particular, let's take the first two equations and set the common factors equal to each other to see that 4x cubed y to the fifth z squared from the first equation has to be equal to 4x to the fifth y cubed z squared. Okay, and again, we don't want to divide out by anything because it could potentially be 0. So instead, I'm going to subtract, and I'm actually going to subtract and also factor out a common factor. There's a 4x cubed y cubed z squared in every term. And what's left over after I subtract is a y squared on the left minus an x squared on the right. And this is all set equal to 0. And this is in factored form, so we can easily read off solutions. So first of all, it's worth noting that x, y, or z could be equal to 0. And I'm just going to say, let's hang on to this for later. let me tell you why I'm doing that. If any of those three variables are equal to 0, we may have a lot of points that satisfy that, but keep in mind, we're going to plug things into the original function and we'll see that those values are equal to 0. So it'll be easy to just pick out if that's a max or min. It's probably not going to be. We're only looking for a max. So as long as there's some point we can plug in on the constrained equation that makes f have a larger value, then these points will be irrelevant. But let's store that information for now and move on to the other part of the equation, which is telling us that y squared equals x squared. If you solve for this in terms of x or y, I'm going to solve for y, you'll get that y is equal to plus or minus x. So this doesn't completely solve the problem yet. We'll need to go appeal to the remaining information to extract more relations between the variables. But no matter what points we find, we know that for this equation to be true, the x and y components have to be equal or a negative of each other. So this really cuts down our possible points dramatically. Let's apply the same approach and take and maybe I'll switch to a different color to stay organized here. I'm going to take the first equation and the third equation, whose right sides are equal, and play those off of each other. So next, let's do 4x cubed, y to the fifth, z squared has to be equal to x to the fifth, y to the fifth. And again, instead of dividing out by things, because I know that x, y, or z could be 0, I'm going to subtract and bring out a common factor. So if I subtract and I see there's a common factor of x cubed, y to the fifth everywhere, left over I have 4 times z squared and x squared. That's all set equal to 0. Once again, x or y could be 0, but I've already really captured that up here, so I'm not going to rewrite that. But here, this information tells me that x is equal to, if I solve explicitly for x, is equal to plus or minus 2 times c. Okay, so now we have a lot of information assembled. We have that y has to be plus or minus the x coordinate, and the x coordinate has to be plus or minus the z coordinate. So actually, as long as we pick a z coordinate, x and y coordinates are determined up to having plus or minus. So there'll be multiple points here for each z choice. But we need to remember one thing. These points have to lie on this sphere, the constraining equation. And remember that these points have to satisfy x squared plus y squared plus z squared is equal to 36. And now let's plug in all of our information. And maybe we'll leave it in terms of z, since that appears to determine everything else. The x coordinate is plus or minus 2z. We'll square that. The y coordinate is just plus or minus the x coordinate. So that could be plus or minus 2z as well. And then z is just z, good old z, set equal to 36. On the left side, I have a whole bunch of copies of z squared. How many do I have? I have 4 of them here, 4 here, and 1 here. So that gives me 9. Z squared is equal to 36. And if you divide and solve, you'll get that z is equal to plus or minus 2. So that's pretty great. That tells us that no matter what, the z coordinate has to be a plus or minus 2. But of course, we knew that the x coordinate has to be plus or minus 2 times that. So we just learned that the x coordinate has to be plus or minus 4. And you know what? The y coordinate has to be plus or minus the x coordinate. So the y coordinate is also constrained. So here are all the possible values where our maximum of the function could occur. And first of all, I just want to remind you, we could have the x, the y, or the z coordinate equal to 0, and I'm going to write those points that way. Or we could have any of the points of the form plus or minus 4, plus or minus 4, plus or minus 2. Those are what come from setting z equals plus or minus 2 and using the things that I circled in purple up above for x and y. This really cut our list down dramatically. There are infinitely many points that satisfy these, but remember that the function value is going to be 0 at all of those. So they probably won't give us max or min. It's just worth keeping track of these. But we have a finite list of points that aren't giving us f equals 0 to go test. So let's work it out. At each of these points on our list, well, first of all, if x, y, or z is 0, f is equal to 0 because it's just the product of those three variables. On the other hand, so, okay, that's probably not a max min, but let's just check to be sure. F of, and notice that this equation doesn't care if x or y are plus or minus, it's raised to an even power for both of those variables. So I'm gonna just reduce our amount of work a little bit and just plug in the two possibilities for z, and then the x and y components can be the plus or minus versions, and we'll get the same answer. So let's see, this is the raising to the fourth is gonna kill the minus sign. So we'll just have 4 raised to the fourth and 4 raised to the fourth. That's actually 4 raised to the eighth from the x and y pieces, and then just times 2. And let's just write this as a power of 2. Let's see, 4 raised to the eighth, that's 2 raised to the 16th. An additional power of 2 will give us 2 raised to the 17th. And if you played that mobile game 2048, that was 2 to the 11th. So you can multiply by 2 a few more times to get whatever this is as an expand, as just some number with some number of tens and hundreds and thousands. I don't remember what it is, and I don't feel like thinking about it, but that's a pretty easy way to write the answer. That's a pretty good candidate for the maximum value. Let's see what happens if we plug in z equals -2. And the x and y components, again, are just going to give us 4 to the eighth. The z component gives us a -2, so this is just going to be the exact same thing with the negative sign up front. So the maximum value is 2 to the 17th, which you can go look up or multiply a few extra powers of 2 after 2048 to figure out. And then the minimum value is -2 to the 17th. And that value of 0, which occurs at infinitely many points where the x, y, or z coordinates are 0, actually was neither a max nor a min of the function. So that's good news. And sometimes different functions could have interesting behavior at those zeros, but in this case they didn't. So we won't worry too much about it today. All right, that's 2 problems down. How much more can we do in one video, you ask? Well, we actually saw a problem. I think this was the exact problem that we worked out in the previous lecture. We can apply Lagrange multipliers to optimization problems more generally. And I'm actually just going to flip over to the tablet to explain how this works and relate things to our previous notions of finding max and min values of functions. But I'm not going to work this entire problem out because we already worked out the answer together in the previous lecture, but I will encourage you to reevaluate your solution using the Lagrange multipliers method. So let's go back to the function f of xy given by this formula here and look at it on the closed and bounded domain D, which is all of the points on or inside of the unit circle of radius 4, whose x coordinates are to the left of the y-axis, or I should specify on or to the left of the x-axis. So x is less than or equal to 0. These are all closed conditions, and clearly I can fit a circle around this stuff because that circle of radius 4 would capture all of these points. So this is a continuous function f on a closed and bounded domain. So the EVT, or the extreme value theorem, tells us that f has a maximum at some point. And more specifically, f has a maximum at a critical point on the interior of D. And to find those, we just need to look at the gradient of f itself and find points where the gradient vector is 0. Those will be critical points of the function or possible max or min values. And it could also occur somewhere on the boundary. So let's break the boundary up into 2 sets. There's the easy part is the strip, the part of the y-axis that's pictured there, which is all x and y coordinates, so that x equals 0 and y is between -4 and 4. And technically, x equals 0 is a constraint. That's telling you that the x coordinate has to satisfy this equation. And that really picks out the line here, which up on the surface f, if we drew this thing, would look like some curve just lying over that small portion of the y-axis. So we could use Lagrange multipliers to evaluate this, where in this case, g of x comma y is equal to x, and that has a really easy gradient. It's going to be 1 comma 0. But it's a lot easier actually to evaluate this using substitution. And we already worked this out in the last video, but if you want to practice again, that's a good one to try. Substitution meaning plug in x equals 0 into our formula for f, shown here, and get an equation just in terms of y. And then for those possible values of y given in our description of that line segment, what are the maximum and minimum values of the function on that strip? Finally, there's one more piece of the puzzle, which is the left semicircle. These are given by, this is given by the following set of points, x comma y in the xy plane, so that they lie, the coordinates lie on the unit on the circle of radius 4, and x is less than 0. So this is a constraint, and this is an extra piece of information that may eliminate some of the points that come out of the Lagrange multipliers process. So I would recommend in this case, this is really g of xy is equal to x squared plus y squared, and it's set equal to 16. I would recommend tackling this full problem again, even if you remember how to do it from the last video, by finding critical points on the interior of the disk, and that gives you a list of finitely many points to test, using substitution to figure out the possible critical points on the vertical line segment part of the boundary, and then using Lagrange multipliers with this circle equation, that's now an equation on the boundary, to find possible critical points on that left semicircle. I'm gonna leave this as an exercise for you to finish on your own. And in particular, if you just want to practice today's new techniques, try to do Lagrange multipliers with the function f given in the problem on this left semicircle. To finish things up, I want to discuss a couple more generalizations of Lagrange multipliers, but this is mainly what we're going to practice together. And to summarize, the main ideas in Lagrange multipliers and in constraint optimization in general allow us to more efficiently solve optimization problems on any closed and bounded domain D. And these are really, there are really 4 steps shown here rather than the 3 that I identified previously. But the procedure here, which you can use in any optimization problem now, is to, in step 0 should be check that the EVT applies, which it should in any problem that you're given. And then to compute critical points on the interior of D involving the gradient of f, and then to identify the boundary components and somehow assign them constraining equations like g of xy equals some constant for each of the different boundary components. Finding the critical points on some of the boundary components will be easy enough using substitution. Like in this problem we just finished talking about, setting x equals 0 is pretty easy. Or if not, you can use Lagrange multipliers in the gradient of those constraining equations g on each of the separate boundary components to identify more critical points. The endpoints of the boundary components will also be of interest and could conceal absolute max or min of the function, so you need to include those as well. And finally, evaluating the function at your entire list of possible max and min values will allow you to identify the actual absolute max and min of the function. So that's our procedure so far. And here's an interesting question that I'll give you an answer to on the next slide. What if in higher numbers of variables, we have multiple constraints? So let's say that we have a function f of x, y, and z that takes values at every point in 3-dimensional space. And let's say that we only want to look at its max and min values on the intersection of some cylinder, shown here in gold, it's a little dulled over here, and some plane, showed here in blue. Where these two intersect may be a curve, shown in black here, but we may not have a good equation for that curve directly. It's easier to express this intersection as all of the points x, y, z that satisfy the cylinder equation and this plane equation, which can be given by 2 different constraints. G is set equal to c, and h is set equal to d for 2 different numbers, c and d. If we have 2 constraints and they intersect in a curve, or they intersect in whatever shape they intersect in, we want to look at optimal values of the function f just on this intersection of the 2 curves. And we're given 2 constraints. So how do we optimize a function subject to more than 1 constraint? And there are a few different possibilities for what happens geometrically. Using directional derivatives, you can show that with 2 constraints, the gradient of f at a critical point of the function on this constraint could be parallel to the gradient of G directly. That would mean that it's just subject to the G constraint, meaning the cylinder, it's already a critical point on that piece of the puzzle. Separately, it could be a critical point on the H constraint, which would mean that the gradient of F is parallel to the gradient of H at the point. Or it could actually be not parallel to one or the other, but it could be a linear combination of the two gradients for G and H. And this actually still gives you possible critical points. If you look geometrically, this would be writing F as a linear combination of these gold and blue vectors, which may point out this way. And for that to be true at the point P on this black intersection curve, the intersection of the two constraining equations would still potentially give us critical points. We want to examine that possibility as well. Using this idea, it's possible to write down the following theorem, which is an extension of Lagrange multipliers. And this will work in higher numbers of variables, and this same idea will work with more numbers of constraining equations, but let's just do it with 2. So if we have a differentiable function f, and we want to optimize it subject to the two constraints that some function g is equal to c, and some other function h is equal to d, then a maximum value and likewise a minimum value, or a point giving a max or a min of the function f that satisfies the two constraining equations has to satisfy the following extended Lagrange multipliers equation, which says that the gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h at that point P, or the g and h gradients are actually parallel, and then it's just enough to check that the gradient of f is parallel to one of them using ordinary Lagrange multipliers. So lambda and mu are two different scalars, and it's usually difficult to solve this type of equation by hand, but in some circumstances it's possible just by using a careful scheme for solving for each of the variables. But lambda and mu can be different, so these are difficult problems in general. You can check that this method is reasonable by counting solutions to equations, and this is technically an observation that belongs to a linear algebra class. But if I have a finite number of equations in the same number of variables as the number of equations we have, you should expect a finite number of solutions in general. And using that observation, for example, if we have this function f in terms of 3 variables, then we'll have 3 components to each of the gradient vectors involved. And our equation setup will look something like this. Sorry, I didn't mean to skip. So our system of equations will look something like this. The first component of the gradient, that's the partial with respect to x, will be equal to lambda times the partial of g with respect to x plus mu times the partial of h with respect to x. And that's one equation in the 5 variables x, y, z, lambda, and mu. And we have similar equations for the y and z components of the gradient vectors. We also have the 2 constraining equations. G is set equal to c, h is set equal to d. This is 1, 2, 3, 4, 5 equations, and we have 5 variables, x, y, z, and the unknown parameters lambda and mu. So in general, we should expect there to be solutions to this and even a finite number of solutions. Although in general, there are lots of situations where no solutions or infinitely many solutions are possible. Here's some summary questions, and I have a few exercises for you at the end of this video. First of all, what is a constraint? When you want to use the method of Lagrange multipliers you learned in this video, what equations do you need to write down? In general, is the set of points that satisfies a constraint closed and bounded? And explain why or why not. And finally, how does a constraint arise when finding the maximum over a closed and bounded domain, like we did in the previous lecture? So to finish, here are a couple problems for you to look at. Here is a graph and a function, and you should identify possible locations of points that maximize this function. And my suggestion for this problem is do so geometrically, using the notion of the direction of the gradient vectors for each of these functions. We can also use the Lagrange multipliers method to show that certain points cannot be max or min values. And for example, the point 3, 3 is not a local maximum of the graph f of xy shown here. That's subject to the constraining equation shown here. And this is something you can work out yourself. I think this is the last one. I'm not going to read the whole slide, but this is a way of comparing two different situations where we maximize a function on a closed bounded domain. That's the first bullet point, or we maximize just on the boundary. And this problem asks you to compare the two situations. Oh, and then there's one more. Finally, here's a function, and we can now fully maximize and minimize this function on the closed and bounded domain shown here. Thanks for tuning in. I'll see you next time.